In this video, we'll go over the in-text questions for sound. And as always, I have already solved or have actually captured the response to each of these questions, and we will go over them one by one. So the first one, how does the sound produced by a vibrating object in a medium reach your ear? So we learned that sound is created by a vibrating object, an object that vibrates. And when an object vibrates, it ends up disturbing the equilibrium of the particles, primarily air particles, of the surrounding medium. And this disturbance is propagated on the other particles in the medium, right, on the other air particles. A vibration has two parts, push and pull. This behavior results in an alternating pressure variation on the nearby medium, and this propagation, when it reaches the ear, we are able to hear. So just like the example of a tuning fork which vibrates, we see that it creates alternating pressure variations because the vibrating tuning fork vibrates the air particles nearby back and forth. So which means that there is a variation. There is an intense pressure and there is a relatively lower pressure. There is an intense pressure, there is a lower pressure, and so on. And as long as it continues and reaches our ears, our ears will be able to sense that, and that's how we hear. Explain how sound is produced by our school bell. So school bell, typically, if you notice, school bell has a hammer which hits another metal, and that causes a vibration. And it is that vibration that is the source of the sound wave. Why are sound waves called mechanical waves? Okay, primarily because sound waves are created because something vibrates. That is the starting point, right? An object has to vibrate, and that vibration would cause the nearby particles to vibrate, the air particles, and it gets transferred, right? So vibration is a mechanical activity, and that is why we call a sound as a mechanical wave. Suppose you and your friend are in the moon. Will you be able to hear any sound produced by a friend? Moon does not have an atmosphere, which means it doesn't have an air, the air particles like what we have on the surface of the Earth. And we know that sound needs a medium to propagate, and unless it propagates, the other person will not be able to hear. So since moon does not have an atmosphere or a medium, sound will not propagate, so I'll not be able to hear my friend. Which wave property determines loudness and pitch? So we saw that loudness and pitch are not absolute properties. These are subjective properties. These are how our ears perceive the actual physical properties. So the actual physical properties that are amplitude and frequency. We saw that the higher the amplitude, which is when the pressure variation is high, we say that the amplitude is high, and when amplitude is high, we see that it's a loud noise, right? And on the other hand, when it is too frequent, when the frequency is high, we say that it is a high-pitched voice. Right? So to summarize, loudness is determined by amplitude, and pitch is determined by frequency. Guess which sound has a higher pitch, guitar or a car horn? Just as we just discussed, pitch is our ear's response to the frequency, and loudness is our ear's response to the amplitude. So guitar has a higher frequency, whereas a car horn is merely loud. It's just as its amplitude is high, it's not its frequency, but its amplitude is high. So a car horn is loud, but a guitar pitch is high because its frequency is high. What are wavelength, frequency, time period, and amplitude of a sound wave? So these are the fundamental characteristics, the absolute characteristics of a sound wave. So as we plot a wave on two axes, as we plot a wave on a graph with the pressure disturbance on the y-axis and the distance on the x-axis. So this is how a sound wave would appear. And we learned that wavelength is the distance covered by a wave to complete one full oscillation. One complete oscillation is the distance between two peaks or crests, or between the distance between two valleys or two troughs. right? So that's what we learned as wavelength. So wavelength is the distance covered by, and this is the distance of one single oscillation. Like one oscillation is a sound wave starting from here and landing here, starting from here till here, and then coming all the way up until here. So this distance is the same as this distance and the same as this distance, right? So wavelength is the distance covered by a wave to complete one full oscillation, and the symbol for wavelength is lambda, a Greek symbol lambda, and it is always measured in meters. What is frequency? Frequency is a number of oscillations in 1 second, right? And it is measured by hertz or second minus 1, because it is number of oscillations by second, and the unit is hertz in honor of the physicist Hertz. Time period is the inverse of frequency. Time period is the time taken by the wave to complete one oscillation. So frequency is number of oscillations per second. Time taken is number of seconds per oscillation. So the unit for time period is seconds, and the unit for frequency is hertz. Amplitude is the height of the wave, which is primarily the maximum displacement of the wave from the equilibrium position, which is the pressure disturbance at that point in time of that wave is what is the amplitude. How are the wavelength and the frequency of the sound wave related to its speed? Okay, so speed is equal to distance over time. So that's how we understood speed as. Now, if you consider one single oscillation, right? If the distance moved by a wave is just one oscillation, right? Which means that by one oscillation it would have covered one wavelength, right? So if you replace distance with the wavelength, and which means that 1 by time is primarily the time taken to complete one wavelength, right? So it becomes frequency. So speed is nothing but wavelength times frequency. So I hope that was clear. Calculate the wavelength of a sound wave whose frequency is 220 Hertz and speed is 440 meters per second in a given medium. Okay, so we just derived that speed is wavelength times frequency. So 440 is equal to 220 into the wavelength. 220 is the frequency, and lambda is the wavelength here. So lambda is nothing but 2 meters. It's 440 by 220, which is 2 meters. A person is listening to a tone of 500 Hertz sitting at a distance of 450 meters from the source of the sound. What is the time interval between successive compressions from the source? So time interval between successful compressions is what we call as the time period. Yeah, it is the time taken by one oscillation, right? So that's a time period, and we know that the time period is nothing but one over frequency, right? And we know that the frequency is 500 Hertz, so it is 1 by 500, which is equal to 0.002 seconds. That's the time period. And this data point is actually redundant. It's not required to solve this problem. The distance is not going to be required. Distinguish between loudness and the intensity of the sound. So yes, we learned that the intensity of the sound was similar to the idea of pressure. Pressure was thrust per unit area, and similarly intensity was sound energy per unit area. And we learned that intensity is related to loudness, but it's just related, but it's not the same, because loudness is a subjective characteristic. It is the ear's response to intensity, whereas intensity is an absolute characteristic of sound, right? And so that's how they differ. And secondly, intensity is a physical quantity and can be measured. Loudness can be perceived differently by different individuals because it is a subjective quantity. In which of the three media, air, water, or iron, does sound travel the fastest at a particular temperature? So we learned that the sound speed is the highest among solids, then comes liquids, then comes gases. So of the three, iron is a solid, so the fastest the sound would travel the fastest in iron. Also, you learned that For the same medium, which is at a higher temperature, the sound will travel even faster. So more the temperature, the higher the speed. An echo is heard in 3 seconds. What is the distance of the reflecting surface from the source, given that the speed of the sound is 342 meters per second? Okay. So let's consider the object to be here, and the sound is propagated in this direction, hits that object, and it comes back as an echo, right? And the echo is heard in 3 seconds. The speed is 342 meters per second. So the distance traveled in 3 seconds is 3 times 342 meters, right? So the sound has traveled 3 times 342 meters. So that's the distance traveled by sound in 3 seconds. And that distance is 2 times the distance, right, that we want to calculate. So this distance plus this distance. So 3 times 342 meters is equal to the two-way distance between the source of the sound and the reflecting surface. So the one-way distance is nothing but 3 times 342 by 2, which is equal to 513 meters. Why are ceilings of concert halls curved? We learned that that is to exploit the property of sound waves because they reflect. So by keeping it curved, we maximize the chance of sound reaching every nook and corner of the hall at different angles, right? So that the sound, so the whole idea is that the sound from reflections can reach the nook and corner of the hall, and everyone can hear, right? There is a good chance that everybody who's seated can hear the proceedings well. What is the audible range of the average human ear? We learned that it is between 20 hertz to 20,000 hertz. Anything less than 20 hertz is called infrasonic sound or infrasound, and anything greater than 20,000 hertz is ultrasonic sound or ultrasound. What is the range of frequencies associated with infrasound? Less than 20 hertz and greater than 0. Ultrasound is greater than 20,000 hertz. A submarine emits a sonar pulse which returns from an underwater cliff in 1.02 seconds. If the speed of sound in salt water is 1531 meters per second, how far away is the cliff? So the idea of the sonar pulse works on the idea of reflection, right? There is a transmitter and there is a detector, and let's consider the ship. The ship is at a distance d from the underwater cliff. So let's assume this is the cliff and the distance is d. So the sound is able to travel a distance of 2d, and it comes back in 1.02 seconds, right? So the time taken to cover 2d distance is 1.02 seconds. So the time taken to cover a distance d is nothing but 0.51 seconds, right? So the depth of the cliff, which is how far away is the depth of the cliff, which is distance d, is nothing but the speed of the distance covered by the sound in 0.5 seconds when it is traveling at 1531 meters per second. So the distance covered by sound in 1 second is 1531 meters, and the distance covered by that in 0.51 seconds is 0.51 into 1531 meters, which is 780.81 meters. So that is the distance. That is how far the ship is away from the cliff. So I think this completes our in-text questions. In another video, let's go over the exercise questions.
One final thing before you leave. If you wish to revise the concepts that you've just learned, please look up and try out the free Revise app bot on Telegram app. Telegram is available for free on both iPhone and Android. Also, if you did like the content that you just watched, please do like, share and subscribe this with your friends. Thank you.